name is Henrik Semb. I am professor and director of the Translational Stem Cell Research Institute at the Helmholtz Center in Munich. I'm Swedish. My science is focusing on understanding how the insulin-producing beta cells form during embryonic development. And we use that knowledge to develop stem cell-based products to treat patients with type 1 diabetes. My hope was primarily, I realized that in 5 years we're not going to solve all the questions, but the goal and the aim of it was to get as close as possible to a product that we will, after ISLET, be able to test in patients with type 1 diabetes. And I think we are going to be able to say that we have achieved that goal, which I'm extremely happy about. The other thing is that I think we've built knowledge around the program throughout Europe, maybe even outside Europe, that it is actually possible to drive programs like this in an academic fashion. And what I mean by that is obviously the science. Everyone knows that there's strong scientists who could contribute to this, but I think the major obstacle have been, can we do this with public funding? I think it advances diabetes research in terms of, in a transparent manner, develop cell products to treat type 1 diabetic patients. And it brings to the table, you know, the challenges associated with that. And ISLET, as I mentioned before, is the idea behind it is that it's going to be a very dynamic, sustainable research program that begin, you know, the cell product we now have established that's going to be tested in patients soon. We will learn a lot from that, and then we have to go back and make a much better product, and you know, continue to improve the product until we have something that's going to be perfect for the patient. So I think the diabetes community, the research community, learn a lot by following ISLET, you know, to understand what the challenges are and how we address them. I would say that the major contribution by ISLET is that we've been able to take the first product all the way to preclinical studies and to be ready to be tested in patients after the end of ISLET. That's you know, it may not sound that much, but all the work behind that is enormous, and I'm really extremely proud of that. Yeah, I've thought a lot about this. I think you know, scientifically it's not difficult. I think the challenge is the commitment, and that you really see it through, right? And that you don't get too discouraged when you realize, oh, you have to do things in another way because the regulatory guidelines tells you that you have to do it this way. As a scientist, we're used to move forward very quickly, and we get very impatient with guidelines or regulations that are imposed on us. So I think that this is really a big challenge in you know, taking it from the bench to the clinics. Yeah, so the key word there is widespread, right? So I think we're already there with, you know, proof of concept that these cells actually works in patients. But the real thing is, of course, the widespread use. And and for the widespread use right now, the major obstacle is to make these cells invisible for the immune system. what we normally call immune evasive or immune protective. And so far the field has focused on trying to put the cells into devices. So the cells would be transplanted with surrounded by some type of membrane that that prevents the immune cells to have access to the transplanted cells. But so far this technology has not worked. You know, there's an enormous amount of engineering work that's been done trying to, you know, engineer material that would facilitate exchange of glucose and insulin across a membrane, but it's so difficult, and you know, if you think about it, it's maybe not so strange, because in the pancreas, in the islets, you know, every insulin cell is in contact with the endothelial cells, the blood vessel cells, right? So and maybe that is completely necessary for the cells to function properly. So what has come up on the radar now the last couple of years are very promising you know, techniques to try to make the stem cells immune evasive. So you can, with genetic means, you can prevent, they can be sort of, as I said, invisible for the immune cells. So far, these there's different strategies, and some of them look very promising in animal models. So what they have shown is that you can have transplant insulin cells from stem cells into an animal model where they would normally reject the cells. But with these genetic tools, the cells are accepted by the host, the animal. So what is happening now is that now there are even some new clinical studies where they try to test if this actually works in humans. Now, if that would work in humans, that's when we have the widespread you know, application.